So imagine for a second that you are blindfolded, right? And you're just dropped out of a helicopter into some completely unknown area of the city.
That is quite the start to a Tuesday.
Right. But bear with me. You have absolutely no idea where you are. And to figure out if you've landed in, say, a commercial district or residential neighborhood, you don't sit there and try to construct some complex mental map of urban zoning laws.
No, of course not. You just reach out.
Exactly. You just reach out, walk around slightly, and identify, like, the 5 closest buildings to you.
Makes sense.
And if you feel around and find 3 houses and 2 office buildings, you logically deduce, hey, I must be in a residential area.
Yeah.
You know, you rely entirely on your immediate surroundings.
Yeah.
And today, we're going straight to the core of how computers use this very primitive human instinct to drive modern artificial intelligence.
It's honestly a phenomenal starting point because when we strip away all the intimidating jargon surrounding machine learning, the actual mechanics of how software makes decisions, they often resemble the most basic, intuitive ways we humans make sense of our environment.
All right.
Like, we assume algorithms require some hyper-futuristic logic, but the foundations are just highly practical.
And that is exactly our mission for you today. We're doing a deep dive into the source material on the K-nearest neighbors algorithm, or KNN, as it's usually called.
KNN, yes.
It is one of the absolute oldest classification methods out there, which I found crazy, like dating back to 1951.
Mm.
And we really want to cut through the dense technical concepts here to understand not just what this algorithm does, but why it matters when we rely on computers to categorize literally everything from text documents to live video streams.
Absolutely.
Okay, let's unpack this. I just used that blindfold analogy to describe reaching out to 5 buildings. In the literature we're looking at, this seems to map directly onto the core function of the algorithm, right?
Oh, it maps perfectly. I mean, the documentation formally calls this a plurality vote.
Plurality vote, okay.
Yeah. So in your scenario, the 5 closest buildings represent what the algorithm calls the K, nearest training examples. That K is really just a positive integer.
Usually a pretty small number, right?
Right, usually small. So the algorithm looks at an unknown object, which is you, standing there blindfolded, finds its closest neighbors, and simply assigns it to the class that is most common among those neighbors.
So if K equals 1.
If K is 1, it just takes the exact identity of the single closest building. No voting needed.
That is, well, the history here is fascinating too, because like I mentioned, this isn't some modern Silicon Valley invention.
Not at all.
The sources note the fundamental concept was actually developed by statisticians, Evelyn Fix and Joseph Hodges, back in 1951.
Yes, and it was later expanded upon by Thomas Cover.
Right. But looking at how it actually functions today, the categorical voting makes total sense. Like, 3 houses beat 2 offices, easy. But I'm trying to picture what happens if we aren't sorting things into rigid categories.
Okay, what do you mean?
Well, say I want the algorithm to predict a specific continuous number, like estimating the property value of a new house based on its neighbors. A house can't be, category $500,000 and just vote on it. The logic seems like it would just hit a wall.
You'd think so, yeah. But what's fascinating here is that the algorithm adapts to continuous variables through a process called KNN regression.
Regression.
Yeah, it's sometimes referred to as nearest neighbor smoothing. So instead of taking a plurality vote of categories, the algorithm just shifts its math. It calculates the actual average value of those K nearest neighbors.
Oh, wow. So it's not actually predicting a new value from thin air. It's just finding a localized compromise of what already exists right around it.
Precisely. So if you want to know the property value of a new house, and you set your K to 5, the algorithm finds the 5 most physically similar houses in your historical data.
Right.
It takes their known property values, averages them out, and assigns that average to the new house. The neighborhood logic remains identical. It just outputs a mean rather than a majority.
Okay, but wait. That raises a massive logistical problem, though.
How so?
You just said it finds the 5 most physically similar houses. How does a computer actually measure similarity or nearness? I mean, if you're measuring a house, you have square footage, which is in the thousands, and then you have the number of bedrooms, which is usually, less than 10.
I see where you're going with this.
Or even worse. If the algorithm is analyzing countries, it might look at life expectancy in years versus GDP in trillions of dollars. If a computer is just crunching raw numbers, that GDP figure is going to completely swallow the life expectancy figure, right? Just because trillions are mathematically way larger than double digits.
You've zeroed in on one of the most critical vulnerabilities of KNN. The computer does not know what a dollar or a year is.
Right, it's just numbers.
Exactly. It just sees a massive number versus a tiny number. So if the features represent different physical units or they just come in vastly different scales, the accuracy of the algorithm severely degrades. The distance calculation just gets completely warped by whichever feature has the largest absolute numbers.
So we have to somehow force all these different measurements to speak the same numerical language before the algorithm even looks at them.
Exactly. The data has to undergo what we call feature-wise normalizing.
Normalizing, got it.
Yeah, we scale the features down so they carry the appropriate weight. Often that means compressing everything into a proportional range, like between 0 and 1.
Oh, okay, so $1 trillion becomes like zero point 0.8, and 80 years of life expectancy becomes zero point 0.8 as well.
Right. And researchers put massive effort into this pre-processing stage. The text actually mentions they frequently use evolutionary algorithms to optimize how features are scaled, or they scale them based on the mutual information they share with the training classes.
Okay, so assuming we've scaled everything properly so the GDP doesn't crush the life expectancy, what kind of ruler is the algorithm actually using to measure this distance?
Well, for continuous variables like height, weight, or distance, it typically uses the standard straight line measurement we all learned in high school geometry, Euclidean distance.
Ah, good old Euclidean distance.
Nice. But the algorithm is highly adaptable depending on the data. If you are working with discrete variables, like, say, classifying text documents, it uses an overlap metric, also known as Hamming distance.
Hamming distance. Okay, I'm picturing that like grading a multiple choice test. You aren't measuring a physical line between two essays. You're just counting exactly how many specific positions match up and how many don't.
That is a highly accurate way to visualize it. It measures the minimum number of substitutions required to change one string of data into the other.
That makes a lot of sense.
And it goes even deeper. In bioinformatics, specifically with highly complex gene expression microarray data, researchers use correlation coefficients as their distance metric.
Like what kind of coefficients?
Things like Pearson and Spearman correlation. As long as you give it the appropriate mathematical measuring stick, the algorithm can find a neighborhood in almost any data set.
You know, there's a behavioral quirk of this algorithm mentioned in the sources that I found just incredibly relatable.
Oh, yeah.
Yeah, it calls KNN a lazy algorithm because it defers all computation until the absolute last second. It essentially just memorizes the training data without doing anything with it.
It's very true.
It totally reminds me of a college student who refuses to study all semester, brings an enormous stack of textbooks to an open book final exam, and then frantically tries to look up the closest matching answers in real time while the clock is ticking.
The lazy learning categorization is completely accurate. I mean, unlike other machine learning methods, there is no explicit training phase where the algorithm builds some complex internal model or decision tree beforehand.
It just sits there.
It just stores the feature vectors and class labels. That's it. The actual mathematical function is only approximated locally when a query is actually made.
But because it's doing this open book frantic search at the very last second, relying entirely on a local vote, here's where it gets really interesting. Doesn't that expose a huge flaw if the historical data is skewed?
How do you mean?
Let's say we have a data set that is flooded with blue squares, just thousands of them, and it only has a tiny handful of red triangles. If I drop a new point right next to a red triangle, but there are 100 blue squares nearby, just because they are everywhere in the system, those blue squares are going to win the vote by sheer volume. The nuance of that smaller group gets totally drowned out by the tyranny of the majority.
That skewed class distribution is a very real problem. The majority class will dominate the predictions simply because they show up more often in that k-nearest neighborhood.
So how do we fix it?
Well, the mathematical solution to this is quite elegant. We use a weighted nearest neighbor classifier.
Okay, so we stop treating every neighbor's vote as equal. How do we decide whose vote matters more?
We assign weights based on proximity. Instead of every one of the neighbors getting an equal vote, which would be a weight of 1 over k, we multiply their vote by a weight proportional to the inverse of their distance.
Inverse distance, okay, meaning the closer you are to the query point, the louder your voice gets in the vote.
Exactly.
So a red triangle sitting right next to me gets a massive megaphone, while the 50 blue squares sitting further away get their volume turned way down, even if they're technically inside my neighborhood.
Exactly. It prevents distant crowds from shouting down the immediate local reality. And the sources also mention another fascinating abstraction to solve this, called a self-organizing map, or SOM.
SOM. How does an SOM physically change the data to fix the skew?
Think of it as creating regional representatives instead of looking at every single individual point, which gives the advantage to the most crowded demographic. The sum creates nodes.
Note, okay.
Yeah, and each node acts as a single representative center for a cluster of similar points, regardless of how densely packed that original cluster was.
Oh, wow.
It essentially levels the playing field by condensing the data into evenly weighted prototypes before the KNN vote is even applied.
That makes the voting process infinitely fair. But that brings us to the actual size of the neighborhood. How do we pick the magic number K?
That is the good question.
Right, because if I ask 3 people, I get a very specific local answer. But if my K is 300, my immediate neighborhood gets completely diluted by the broader city.
You've hit on the core tension of tuning the algorithm. Larger values of kin definitely reduce the effect of random noise because you're taking a broader consensus. But you're absolutely right that it makes the boundaries between different categories a lot blurrier.
So is there a rule of thumb?
Well, if you are dealing with a binary classification problem, meaning there are only 2 possible categories to choose from, you must choose an odd number for K.
Oh, to prevent a tied vote.
Exactly.
Because if K is 4, you could end up with a 2-to-2 split and the algorithm just gets stuck.
Precisely. And to find the empirically optimal K, researchers often utilize what's called the bootstrap method. They repeatedly resample the data, estimating the accuracy of different K values, until they find the mathematical sweet spot that balances noise reduction with distinct boundaries.
Okay, I want to circle back to the lazy learning concept for a second, because I just can't shake the logistical nightmare of it.
The open book test problem.
Yes. If the algorithm doesn't build a streamlined model in advance, and it just calculates the distance to every single stored example at the very last minute, what happens when the data set is massive?
Yeah, that's a problem.
I mean, if I have 1 million data points, and each point has dozens of features, searching through all of that in real time seems like it would just crash a computer.
Oh, it absolutely would. And this introduces one of the most dramatically named concepts in all of data science, the curse of dimensionality.
The curse of dimensionality.
Mm.
Honestly, it sounds like an Indiana Jones artifact, but I'm guessing it's a mathematical trap.
This raises an important question, right? Because it is a severe trap. When you start adding too many dimensions to your data, usually once you get past 10 dimensions or features, the very concept of Euclidean distance begins to physically break down.
Wait, I'm struggling to picture how distance just breaks down. A foot is a foot, regardless of how many things you're measuring, right?
Not in high-dimensional space. Imagine a standard 3D room.
Okay.
There's a clear center, and there are corners. But as you add dimensions, say, you stretch it into a 100-dimensional room, the mathematical volume of that space expands exponentially. The geometry works out such that almost all the data points get pushed to the outer crust of that space.
The crust.
Yeah, the center becomes virtually empty.
Oh, wow. So if my query point is in the middle of this 100-dimensional room, practically all the historical data points are pushed out to the walls, meaning they're almost exactly the same distance away from me.
Exactly. When every point is roughly equidistant from the search query, the concept of a nearest neighbor becomes mathematically meaningless.
Because everyone is equally far away.
Right. The algorithm gets paralyzed because nothing stands out as being closer than anything else.
So if the data has too many features, the algorithm essentially goes blind. So how do we break the curse?
We have to aggressively simplify the data using dimension reduction. Before we ever apply the KNN algorithm, we transform the data to extract only the most critical information, creating a low-dimensional embedding. The sources cite techniques like principal component analysis, or PCA, and linear discriminant analysis, LDA.
I hear terms like principal component analysis a lot in AI discussions. What is that physically doing to the data to solve this dimensionality problem?
Think of it like taking a 3D shadow of a complex object. If you have a highly complex, multidimensional shape, PCA essentially shines a mathematical light on it to cast a flattened shadow.
Okay, I can picture that.
It squashes the data down so you only keep the most distinct, important outlines, the principal components, and it throws away all the useless depth and noise that's just confusing the algorithm. The text gives a great real-world example of this in a computer vision pipeline for face recognition.
Like how facial recognition unlocks a smartphone.
Yes. You cannot run KNN on millions of raw, high-definition pixels. That's way too many dimensions.
Right.
So the pipeline starts with a hair face detection algorithm just to locate the face, uses mean shift tracking to follow it, and then crucially uses a PCA projection. It compresses that incredibly complex visual data down into a manageable feature space.
Oh, so only after the face is flattened into its core mathematical shadow is the KNN classification applied to identify who it actually is.
Exactly.
So we solve the dimensions problem by squashing the features. But what about the sheer volume of the data? Like, squashing the features helps, but if I still have a billion individual records, the last-minute open book search still takes way too long. Do we just, I don't know, randomly delete half the historical data and hope for the best?
Not randomly, no. We use data reduction techniques to systematically eliminate stored examples. A classic method mentioned in the text is the condensed nearest neighbor rule, or CNN, also known as the HART algorithm.
Okay, so how does the HART algorithm decide what gets kept and what gets thrown in the trash without ruining the accuracy?
It looks for what we call prototypes. Essentially, if a data point is sitting completely surrounded by other points of its exact same class, it's considered an absorbed point.
Absorbed.
Yeah, it doesn't offer any new information for drawing the boundary lines between categories. It's redundant, it's safe, and obvious. So the algorithm deletes it. It prioritizes keeping points that have a high border ratio.
Border ratio, meaning we want to keep the data points that sit right on the turbulent, messy edge between two different classes.
Precisely. Those boundary cases are the most informative for making future decisions. The safe echo chambers in the middle of a cluster are just noise. By tossing them out, this algorithm can sometimes reduce a data set to just 15 or 20% of its original size while maintaining full accuracy.
Keep the edge cases, throw away the echo chamber. I absolutely love
That's
that.
very efficient.
Now, we've spent this entire time talking about how KNN uses similarity to find its neighbors. But the source material mentioned a variant that flips this entirely on its head, and I found it fascinating. The furthest neighbor variant.
Ah, yes.
Instead of finding what's closest, the algorithm actively seeks out maximal dissimilarity. It looks for the total opposites. Why would we ever want an algorithm to actively seek out things that don't belong?
It has a highly creative application in recommender systems. It's used to build what's called an inverted neighborhood model.
So instead of a streaming platform doing the standard, people who like this movie also like these exact same movies, what is the furthest neighbor doing?
It identifies the users who are the absolute most dissimilar to you, and it uses their preferences inversely to generate your recommendations.
That's wild.
Now, historically, furthest neighbor methods achieve lower predictive accuracy. They aren't going to perfectly guess your next favorite movie, but what they do achieve is a massive increase in novelty and diversity.
Oh, to break you out of the echo chain.
Exactly. They are designed to break you out of your algorithmic filter bubble by recommending things that the traditional nearest neighbor method would just completely ignore for being too weird or unpopular.
An algorithm mathematically designed to give you a surprise. That's great. Are there other ways we use this to find the weirdos in the data?
Yes, actually. KNN is also highly effective for anomaly detection. The mechanism is incredibly simple. If we measure the distance to your K nearest neighbor, and that distance is massively large, it tells us that your local density is very low. You are sitting out there entirely by yourself.
You're a statistical outlier.
Exactly. Despite being such a simple foundational model, using KNN for finding anomalies and outliers works remarkably well. It even holds its own against much more complex modern data mining methods.
So what does this all mean? Let's tie all of this together. We've gone from blindfolded people feeling houses to flattening faces into mathematical shadows.
We have covered a lot of ground.
At its core, KNN is this brilliantly simple concept from the 1950s, the idea that you are who you hang out with, mathematically brought to life. We've explored how it uses plurality voting, how it survives skewed data by turning up the volume on the closest neighbors, and how it survives the absolute nightmare that is the curse of dimensionality by squashing data down to its most useful prototypes.
And if we connect this to the bigger picture, understanding these mechanisms, how algorithms handle noisy data, skewed populations, and border cases, it's vital.
Yeah.
It isn't just an academic exercise. It gives you a framework to think critically about how software is categorizing your own digital footprint every single day and why it might be making the assumptions it makes.
Absolutely. And as we wrap up, I want to leave you with one final thought to mull over. And this builds directly on something kind of hidden in the source material regarding the one nearest neighbor classifier.
Oh, the simplest version?
Right. This is the absolute simplest version, where k equals exactly 1. You only look at the single closest point.
Ah, you are referring to the Bayes error rate property. It is one of the most profound mathematical proofs in classification logic.
It really is.
Yeah.
Because the math shows that as your historical data set grows and approaches infinity, simply using the one nearest neighbor rule guarantees an error rate that is no worse than twice the Bayes error rate.
Which is huge.
Right, for context, the Bayes error is the theoretical minimum possible error you can ever mathematically achieve. Think about the philosophical weight of that for a second. We constantly assume that making the best decision requires a complex consensus.
Yeah, a committee.
Exactly. We assume we need a weighted average of hundreds of different opinions or a massive convoluted decision tree. But this mathematical proof says that's not necessarily true.
It challenges our entire assumption about what constitutes intelligence in decision-making.
Right. With enough historical experience, with a massive enough memory of past data, simply looking at the single closest past example gets you incredibly close to the absolute best possible decision you could ever mathematically make.
It's pretty mind-blowing.
Does that mean having a massive, perfectly preserved memory of past experiences is actually more effective than having a highly complex reasoning process? If you're blindfolded in the city, maybe you don't need to feel 5 buildings to know where you are. If you've been to enough places, maybe you only need to touch one wall. Thank you so much for joining us on this deep dive. Keep questioning the algorithms, keep exploring the data, and we'll catch you next time.